let's determine an alternate classification which you can use to label the axes of the Hertzsprung-Russell diagram. It's the same information, but instead of tracking it by temperature and luminosity, you track it by two other parameters which are just different measures of the temperature and luminosity. So let's introduce ourselves to these two alternate parameters. So this is alternate parameters. So if we have the Hertzsprung-Russell diagram, the HR diagram, then on the horizontal axes, we are tracking temperature. And we start tracking at 3,000 degrees, and we end up tracking at 30,000 degrees. And on the vertical axis, we do the luminosity, one solar luminosity, all the way up to 10 to the 6th, and all the way down to 1/10,000th of a solar luminosity. Now, there is another way that we can measure the temperature of the surface area of a star, and that is we can examine the spectrum that it sends. Because in the atmosphere of the star, there are elements, atoms. And when the atoms bump into each other via collisions, they transfer energy. And as they transfer energy, then they kick their electrons to higher orbits. And then the electrons come back down, and as they come back down, they send a certain wavelength. And that wavelength tells you how high they had been kicked up. Now, the higher the temperature that's on the surface, the higher the orbit that those atoms are going to kick each other's electrons up into. So all we need to do is measure the amount of wavelength or frequency in the spectrum that's coming off of an atmosphere, and we can then use that to tell us what was the surface temperature. Because we know that the higher the surface temperature is the higher the orbitals that the electrons would be kicked into, and as they fall back down, they're going to emit a frequency that is a signature of the orbital that they were in. So when we look at the spectrums of all of the stars, then we can go a one-to-one correspondence between the type of spectra that we're looking at, in other words, what elements are jumped into what orbits, and the temperature of the star itself. So we have classified the spectrums that would come from stars into, oh, be a fine girl, kiss me right now, into 9 different spectral types. And each spectral type is reflective of a different temperature. So the very highest temperature stars generate a spectrum that we call type O. The next highest temperatures generate a spectrum that we call class B. Then a F, then a G, and then a K and an M. Now, our sun is right here, and it's right there. So our sun has a 6,000 degree surface temperature. It has a 1 solar luminosity, and you see it's right under the G. So our sun is of a spectral type G. Now, we also have between each one of these letters 10 subdivisions. And you have a lower number depending on whether the star is hotter or not. In other words, a G2 is hotter than a G3, and a G3 is hotter than a G4. And our sun happens to be a spectral type G2. That means it is emitting absorption lines that are reflective of a surface temperature that would cause its electrons to jump into certain orbitals that are reflective of 6,000 degrees, and we call that type of spectrum a spectrum of class G. Now, there is difficulty among students remembering this, so there is an acronym for remembering it. It says, "Oh, be a fine girl, kiss me." Or if you want it the other way, "Oh, be a fine guy, kiss me," is the way that it can be remembered. Now, how do we classify the magnitudes in an alternate way? Well, what we do is look at the 4 brightest magnitudes, and we simply specify them by Roman numerals 1, 2, 3, and 4. So these correspond to the luminosities that are matched up on the other side. The very brightest stars, the highest luminosities, are called a luminosity class 1. And next to that is a class 2, a class 3, and a class 4. And our star, and all the others that are not in that type of a classification are classified as class 5. And all the stars in the main sequence are classified as class 5. These other classifications, 1 through 4, refer to stars that are not on the main sequence. If it's on the main sequence, it's a classification 5. If it's not in the main sequence, it's a classification luminosity 1 through 4, depending on how bright it is. Now, these classes are determined also from the spectra of the stars, because if the absorption lines are very, very thin, that means that there is a lot of unification inside the motions of the star. The atmosphere is very thin, and it is a very hot star, class 1. But as you come to lower magnitudes, the atmospheres get denser. And as the atmospheres get denser, then there's a spread of the velocities that are in the atmosphere. And because there's a spread in the atmosphere, then there's a Doppler shift. Some of the electrons, some of the atoms are moving towards you, some are moving away from you. And this Doppler shift will tend to widen the absorption line, because it will have a red end and a blue end, as well as the part that's in the middle. So as you come down in temperature, then the absorption lines get wider, and that's what you use to classify them in classes 1, 2, 3, or 4. And you use the elements that are present and the orbitals to which they're kicked in to classify it into a spectral class, O, B, A, F, G, K, M. Now, our sun is a type G2 according to its spectral class, and it's a main sequence star, so it is called a G25.